Very good evening, everyone. Hope you're all well. Welcome along to this evening meetings. We'll be getting underway in about 10 minutes time. So I've just put some live views of Mars for you from my Celestial on C11. So do enjoy those until we get going. See you in a couple of minutes.
Welcome everybody to the Plumtree meeting of November, where James and I are going to be talking about double stars and what you can see in the sky and a whole plethora of things about double stars. It's a double star, double star. So we're going to talk about, we're going to have a look at the double star first, and there's a double star just in case. It's such a good animation that we have to include that. So the objectives, we're going to talk through what are double stars, a bit about the history of observation of them, why we observe them, what they can tell us, and how to observe them, and a few other bits and pieces sprinkled in. So we'll start with some basics, define what a double star is. So as the name implies, a double star is two stars that appear to be connected, at least in the eyepiece. So either with the naked eye or with an optical aid, and they may be associated with each other or they may not. So there are two main classes. There are actually binary stars and there are optical doubles. And to explain that a bit more, we've got some sort of cartoon pictures here. So this is a double star. As you can see down at the bottom is what you see through the actual telescope. The blue and the red star appear next to each other. And as we can see from the sort of bit on the top right, that these two are actually two stars that are connected, probably gravitationally and probably orbiting each other. So they not only appear to be associated with each other as a double star, but they are actually a double star system. Now you can also have an optical double star. In this case, through the eyepiece, they look exactly the same. But in reality, as you can see from the picture above, if you could see it from the side, which we can't, they're actually a long way separated. And it's really just an optical illusion that you can see the two stars as though they appear together. So there's been an interesting topic throughout the history of astronomy, is untangling these two, because obviously with a two-dimensional view, they both look a bit the same. Illustrated nicely by this image here of clearly set up that these things are all not in the same plane, that the Eiffel Tower is a long way behind these two people, but it appears in the photograph that they are all just associated with one another. And we can have either a binary system where they are gravitationally connected, or an optical double, as we said. Just a quick note about if you were actually on a binary system, and the classic was obviously Tatooine from Star Wars, where they live on a planet with two suns. So this is actually quite possible, and we have found some double star systems with exoplanets. So we do know these things exist. And there are actually three variants of this that you can exist. So this one, Tatooine, is actually going to be the second one. So the first one is known as the satellite type. So in this case, you have a central sun with a planet going around it. That's this blue thing in the red orbit. And then you have another star, which is maybe a reasonable distance away or a very long distance away. This is certainly the case with Alpha Centauri, where Proxima Centauri, which we know has a planet now, is actually quite a long distance from its other companions, Alpha Centauri A and B. So that's an S-type or a satellite type, where the second sun is a satellite of the first one. You can also have a planet type, which is the Tatooine case, where you have a planet that's orbiting two stars, and the two stars are relatively close together, and they orbit around each other or around a common center of mass. And then you have the main planet, or this planet in this case, Tatooine, going around the two, so you see the two stars rise and set from your vantage point on the planet. And there is a third, which is a much rarer case, and this is an L-type, where you've got a locked planet. So in this case, you've got the central star in yellow, another star in red orbiting around it, but you've also got a planet which is locked in place by the gravity of the first two. So it's always exactly opposite the red star in a place called a Lagrangian point. So if it happens to fall into that position, it tends to stay there because it's a sort of gravitationally favorable state. So with the basics out of the way, how did it all start? James.
Right, so I'm going to cover some of the basics of double star astronomy. Oh, let me go back a slide. So there's lots of information on the internet and papers which are freely accessible. Now, there are a number of double stars which are visible to the naked eye, so you don't need binoculars or telescopes. There aren't that many of them. Mizar and Alcor are a common one, which we're going to talk about in a moment. But there isn't much documented about double star systems or what people thought of them prior to the invention of the telescope. Here we go. Mizar and Alcor, these are in the constellation of Ursa Major. They're a naked eye double. And when you look at them, they're about 12 arc minutes apart. And we're going to come back to what an arc minute is shortly. And in various cultures, they've been referred to as different things, but one is the horse and rider. Clearly, Mizar being the horse and the smaller participant, Alcor being the rider. And people often say this is a test of eyesight, whether you can split them. And again, we're going to come back to that in a minute. Here we can see a wide field shot of the asterism of the Big Dipper in Ursa Major. I'm just going to put some lines in to show the outline of the Big Dipper. There's the handle on the left and the pan on the right. And Mizar is this middle star in the handle. And if you're close enough to the screen or your eyesight's good enough, you might get the hint that there's more than one star there. If we zoom in a bit closer, you can now see it looks a bit like a snowman with a small head and a bigger body. We get really close on this image and you can see the brighter Mizar at the bottom and Alcor at the top. Now, if you were to point a relatively low power eyepiece at this star, this is what you would see. And the first thing people think is the two at the bottom. These two are Mizar and Alcor, but actually they're not. The bottom one is Mizar and the top one is Alcor. And you can see that Mizar itself is actually composed of two stars. So with the naked eye and with binoculars, this pair looks like a double. In fact, they are. But then with a telescope, you can see Mizar itself is actually a double system. Now, there's a little star here called Ludwig's star, which in about 1722, the notes have vanished. I think Julian's got the notes. 1722, this star was spotted and was thought to be a planet, but subsequently determined not to be. That's an interesting story in itself. So in about 1617, Benedetto Castelli is the first person to have recorded an observation of a double star through a telescope, and that was Mizar. So 1617, so that's just a few years after the invention of the telescope. By 1779, this chap Christian Mayer produced a small catalogue of doubles. He was thinking these stars were actually related to one another, but another expert at the time contested this and said, "Will you produce a catalogue of all these stars, and then other astronomers can observe them and see if they are binary systems related to one another, or if they are just optical doubles and the fainter star is just a coincidence, a background star." And this is about the time that William Herschel got involved of discovering Uranus fame. He initially believed them to be optical doubles, and he was going to use them to study stellar parallax. But during his investigations, he became convinced that some of these pairs were actually associated with one another. They weren't background stars. And then the question really comes about that time is, well, how close are these two as viewed from Earth, and potentially, if they are related, how close are they in reality? What's their absolute association? So curiosity, you know, this is fun looking for double stars. They're pretty colours. you can test your equipment, soon turned to scientific pursuit. By the early 1800s, there had been several catalogues produced of double stars. At this stage, still unclear if they were binary doubles or optical pairs, and about 3,000 doubles were known. By the end of the 1800s, about 10,000 doubles were known, and this is at the point where the big aperture telescopes were coming online in America, Australia, South Africa, Russia. So optics were improving, aperture was improving, so more and more could be determined. So today there's over probably 150,000 known doubles. Maybe 50% of all stars are doubles. Julian can probably comment on this later. There's still very active amateur involvement in double star astronomy. People do it for fun, but also people are making observations and submitting them to the Journal of Double Star Observations and also the British Astronomical Association. But you might ask why, what's it all about? Well, in fact, characterizing the orbits of these binary systems is very useful. It allows people to calculate stellar masses and also make predictions of the radii and the density of these stars. So with a lot of areas of amateur astronomy, the amateur is still contributing very valuable information. So angular measurements. If we think about a circle, that's made up of 360 degrees. And if we just take one of those degrees, that in itself is made up of 60 arc minutes or minutes of arc. And that's often written as 60 with a single not exclamation mark. What's the word, Julian?
Quote mark.
Quote mark.
Quote.
Single quote mark. And if you take one of those arc minutes, that in itself is made up of 60 arc seconds, and that is written with 60 and a double quote mark. I always remember second, like 2, so that's got 2 quote marks. So 1 degree is made up of 60 times 60, 3,600 arc seconds. And obviously you'd have to multiply that by 360 to work out how many arc seconds there are in a circle, but there's a lot. And if we think about things in the sky, we know the moon and the sun appear to be about half a degree in diameter when they're full. The sun's always full unless it's being eclipsed. So half a degree is 30 arc minutes. And then these planets aren't to scale. It would be nice if they were that big, but they're not. This is just to show the planets, and these are all images I've taken. So Jupiter at its biggest is about 50 arc seconds, Mars about 25, Saturn 20, and that's the Ring Nebula, which is about 1.4 arc seconds. And if we go back on the right now to Mizar and Alcor, so Mizar's at the bottom, and it's split into Mizar A, the brighter one, and Mizar B, the fainter one. We actually know that they're about 12 to 14 arc seconds apart. So if we were to place Saturn in that field of view, if that was possible, Saturn's never in that position. That's how big Saturn would appear. So, oh yes, resolving power of the human eye. So this is another sort of basic we need to think about. So theoretically, human vision is has the potential to resolve less than 1 arc minute. And when you do the Snellen test at the opticians with the letters on, 20/20 vision is probably about 1 arc minute. And some people have eyesight which is better than 20/20, other people have it worse. And interestingly, I was researching 20/20 doesn't mean normal. It was just an arbitrary value that Dr. Snellen came up with at the time. So there are plenty of people who have better or slightly worse than 20/20 vision. But in practice, in astronomy, there are lots of reasons which mean the human eye can't always determine or differentiate 1 arc minute. And so it's generally 2 arc minutes at best, but probably nearer 3 arc minutes for most of us. So Julian's going to talk about some basics in optics.
Right, thank you, James. So what we start off with is the basic problem we have in optics is that a single point source, which is like a star, so if you try and focus in on a star, you never actually focus entirely that point of light. This is just one of the restrictions of optics, that instead what you get is something that you see on the left. You get a central very bright point, which is the star, but then you get these concentric rings of sort of scattered light that is associated with the star. So if you're trying to zoom in on a double star and actually split it into 2 components, this is what's going to catch you out in the end. This is called the Airy disk because it was discovered by, is it George Airy? Can't remember. Yeah. So he made the initial sort of investigation of this and said, well, yes, this is how light spreads out. And if you'd like some maths, which I'm sure you'd all love, this is the actual equation that governs it. So it's a fairly straightforward equation. So sine theta, which is this bit over here, is just how big this blob of light is going to be. And this is given, this is based on 2 things that you're looking at. One is the wavelength of the light that you're looking at. So for optical telescopes, that doesn't really vary much. Red light is much the same as blue light, pretty much. I mean, they are different, but not substantially. It does make a huge difference, though, if you go to something like radio waves or X-rays, then this makes a big difference. So you can sort of ignore the top bit. The bottom bit, though, is the important bit, which is the size of the aperture. And this is why big telescopes are kind of better than small telescopes. This is why people put a lot of money into buying bigger telescopes, especially the professionals, because the bigger you can get the aperture, you can see this bit is on the bottom of the equation. So the bigger this is, because it's on the bottom, it makes this whole thing smaller and therefore makes this whole thing smaller. So this blob, this series of rings gets much smaller with the bigger the aperture. So, you know, if you've got a 5-inch telescope, that's going to give you one size. But if you go up to 10, then that suddenly shrinks it down and you can actually split 2 stars much better. And then if you go up to like 0.5 meter or 1 meter or 8 meters, then you're going to improve and improve upon that as you get better and better. Now, another one is the Dawes limit, and this says how many arc seconds you can see. And this is, again, a fairly straightforward equation. So the bit on the left-hand side is how many seconds of arc. So R with the double quotes is how many seconds of arc you can distinguish. And there are 2 equations. One is if you're working inches, it's 4.56 divided by D, the diameter of your aperture, or 11.6 if you're working in metric. So that's effectively the angular resolution that you can see between 2 stars. If they're going to be closer than whatever that comes to, you won't be able to see the difference. They'll appear as 1 star. Now, this is great. So we could just go on building bigger and bigger telescopes, which is what we do indeed do. You know, the biggest ones in the world at the moment are about 8.5 meters across in the mirror. The next generation are going to be 20, 30 to 40 meters across, which is a huge thing. So that's making this D much, much bigger. So they will be able to see with even much more precision. However, life isn't that kind to us, really. So the other thing that's limiting us is the what we call the seeing, which is just how much the atmosphere is moving. And you can see this nice picture of the moon from James. You can see it wobbling there. And that's not because the moon is wobbling or boiling, that's just the atmosphere is moving. And as the light comes to us, it's taking slightly different paths as it goes through slightly different hot and cold bits of the atmosphere, all acting as tiny lenses and moving it around. So you can get up to a certain size with this area and the doors limit by just building bigger and bigger telescopes. But sooner or later, you're going to get stuck by the atmosphere. The atmosphere is going to limit what you can see because it's all just shifting around. So if you're taking a 5-minute exposure of something, it's going to have wobbled around all over the place in that 5 minutes and will have blurred it all together. So most smaller telescopes are diffraction limited, and so they would benefit from you buying a bigger mirror up to a certain size. But the bigger ones are now seeing limited. So when you get to the professional sized ones, they're very much limited by the atmosphere. So having a bigger telescope gives other benefits too. You can capture light quicker. So if you're looking at a very dim object, you can get a spectrum of it or something like that. But if you're trying to look at the fine detail, you're going to be defeated by the atmosphere. And there are two ways you can get around this. One is to get rid of the atmosphere. Now you can do that partially by moving up to the top of a high mountain, or you can do it completely by moving out into outer space. The former is reasonably cheap. The second is quite expensive to put a big telescope into space, partly because you're limited in what you can squeeze into the nose cone of a rocket. And the other way is to try and get rid of the atmospheric shimmering by stopping it shaking around. And people have tried various things to do this. Notably, Fritz Zwicky, famous astronomer, he was at one of the California telescopes one night when it was shimmering around, and he wondered whether firing a rifle bullet up the trajectory of the telescope would smooth out the seeing. So they apparently did that, and it had no effect. But that's one way you could try. It doesn't work. The more modern way is to fix on a particular star that you know should be stationary, and then you see it wobble around with the atmosphere, and then you get a computer to say, well, that star should be absolutely rock solid, but it's moving around. So what can I do to stop that star wobbling around? What distortion can I make to the mirror to stop it wobbling around? And so with a very quick feedback loop, it takes a picture of the star and sees how it's wobbling, and then it undoes that by quickly altering one of the mirrors to take out this wobble of the atmosphere. So this is usually done either with a guide star or quite commonly now with lasers. So you shine a laser up into the upper atmosphere and make your own guide star. And then you can take that out. This works pretty well because the atmosphere shimmers on about a time scale of a few milliseconds. So if your computer works and your mirrors can work faster than a few milliseconds, perhaps 100 milliseconds, something like that, then you can work fast enough to take this out. So with that, let's have a look at some definitions of binaries. So a visual binary, so this is slightly different to the ones we covered before. So a visual binary is exactly what it says on the tin. The ones like Alcor and Mizar we've just seen. You can clearly see there are two stars there. It's just a question of getting a big enough telescope to split the stars up into their separate parts. So that's the first case. But you can also find binaries where you can't see that. So that's the next sort. So this is a spectroscopic binary. These are two stars that are going around each other, but they're far too close, or they're just too close for the resolving power of the telescope you're using, so you can't actually see the two. But if you take a spectrum of them, so you see these lines here in the spectrum. So normally it would be like this. You'd see the fixed lines of perhaps hydrogen in the spectrum, and they would stay there. But with the spectroscopic, one of them is coming towards you, and one of them is going away from you at any particular time. And this shifts the spectrum very slightly. So in this case, we've got A coming towards us, so it's shifted slightly towards the blue, and the red is going away from us, and that shifted slightly towards the red. So you suddenly see, well, you don't suddenly, because they don't move that quickly, but they start to split the spectrum. So where you would normally see the single hydrogen line, you start to see two hydrogen lines, and then if you observe them for long enough, they will come together again, and then split apart again in a different direction as they orbit each other. So that's a spectroscopic binary where you can't actually see the two. But in this case, we've actually got, this is what was a spectroscopic binary, but now got a huge telescope on it, and have actually confirmed that it is two stars. But even then, you can see it's really quite blurry because it's very much at the limit of resolution. Oh yeah, that's who took it. First image again. Another type is eclipsing binaries. So this is two stars going around each other and one covers the other. So again, you can't actually see the two stars, or not normally at least, but if you watch the light coming from it, you can see there it goes long and then it suddenly dips down as one obscures the other, and then a slightly smaller dip as the smaller one goes in front. So again, you can't actually see the two stars, but you can infer there are two stars there by looking at the light curve and see that something something like this is happening. Incidentally, this is the same way, or at least one of the mechanisms they find planets around distant stars. It's just stars are really big things, so you get a really big drop in light. Planets are much smaller, so you see considerably smaller. Another class is called astrometric binaries. So in this case, you're watching the star as it moves across the night sky. So all stars tend to have a proper motion. So they move with respect to other stars very, very slowly across the sky. There's one or two that move a little quicker than others. But over many years, they sort of move. The ones that are closer to us will actually have some movement. But often it's not a straight line, as in this black line here. It's actually a wiggly line like this. So sometimes it's above or below where you would think it should be. So this is just by careful charting of the star, watching how it moves and seeing it doesn't move in a straight line. So we can now infer there is something tugging on it that is making it move in this sort of wiggly line. So it's almost certainly in orbit around a smaller star or something else. I mean, in the case of something that you wouldn't be able to see, such as a black hole, would also have the same effect. So with that, let's go back to James and how to measure a double.
Right, so back to amateur astronomy and how we can go about measuring doubles. So we've got a new double star now in the field of view, and there are two things to actually measure. The first is the separation. So that is how far apart are the two stars, and we measure this in arc minutes or arc seconds. And the other thing to measure is something called the position angle, or PA, and this is in degrees. And for this, we need to know where north is in the field of view. So if you were to push your telescope towards the North Celestial Pole, you'll see which way the stars move, and that is where north is. And what we need to measure is the angle, like a clock face, between north from the primary star and the position of the other star, and we have to go through east. Now on this image you can see east is on the left because the image is obviously flipped for this type of telescope. So we need to measure the angle from north to the secondary star through east, and on this star it's about 135 degrees, because if it was due east of the primary star it would be 90 degrees, and this has got a bit more added on. So how to measure this? The first measurements were taken with a filar micrometer. So filar means filament, and the stories about William Gascoigne. A spider had put a web across his eyepiece, and when he looked he could see this web illuminated by starlight, and that gave him the idea to invent the micrometer. Now this one has got a fixed filament and another filament which can move using this dial here, and that the more you move it, then this gauge here will tell you by how many microns you've moved it. And the idea is to put one star under the fixed filament and then move the dial until you get the other star under the other filament, and then with some fancy calculations and a lot of patience you can work out the angular separation in arc minutes or arc degrees. arc seconds. Now, the other method is if you've got fixed filaments, so you can't adjust where the filaments are, and you turn the motor off on the scope, on the mount, and then the stars will slowly drift across the field of view over a period of seconds, minutes, depends on the field of view, and you can time how long it takes, say, the first star and the second star to cross, what the interval is. And we'll come back to how you use that drift method in a minute. More modern ways of doing this is with something called an astrometric eyepiece. Now, in the past at Plumtree, we've talked about illuminated reticle eyepieces, which have got crosshairs on, and this little arm at the side with batteries and a little LED, which illuminates the field inside. And they're very useful for finding the center of the field of view and for accurate go-tos and drift aligning and things. But this astrometric eyepiece is a bit more advanced, and it's got a fancier reticle inside. And here you can see it's got degrees on the outside. It's got a 0 to 50 scale across the middle. It's got sort of a target here, which is for manual guiding if you're doing that. And again, like a protractor here with 0 to 90 each side. And what the idea is here is to put, again, the primary star in the center. So the position angle is relatively easy to sort out. So what we need to do now is to work out the angular separation. And again, what we can do is put the primary star on this scale, and that's at about 25 units. And the secondary star is about 10 units. So the interval between them is 15 units. Now, the problem is we don't know what these units represent. They're certainly not arc seconds or arc minutes. So what we need to do is, again, to stop the motors and allow these stars to drift over the field of view, and we need to time that. And then that will give us an idea of what this scale of 0 to 50 represents. Now, we know stars drift at a rate of about 15 degrees an hour. So if you're mathematically minded, you can do some calculations and work that out. So what I've done on this website is to plug in my Celestron C14 and the 12mm eyepiece of the astrometric eyepiece. And this tells us that the field of view is just about 9 arc minutes. And we know that stars are traveling at 15 degrees an hour, so you can do some calculations and work out that it would take a star 40 seconds to cross the field of view of this eyepiece in this telescope. And then we can work out the what each of those units represent and work out the angular separation, position angle, and the angular separation of those two stars. Now, there are other methods. You can use CCD cameras and then reduce your data subsequently. There are other methods still, but these are the commonest ones for amateurs. Right, Julian's now going to tell us about some weird and wonderful binaries, hopefully.
Indeed. So there are all sorts of classes of binaries that at least theoretically possible and indeed have been proven to be so. So you might wonder, well, how close can two binary stars get? And the answer is actually very. So we can actually have, these are almost two variants of the same thing. You can have contact binaries. This is two stars that are orbiting each other, but they are actually in contact. So if you sort of followed from the center of the star out to the edge and then onto the next star, there wouldn't be any space in between. They're actually orbiting close enough that they contact each other. And this is enhanced because the gravity tends to pull them out into sort of egg-shaped stars rather than circular spherical stars. So these would be going around with a always contacting. And you can actually tell this from, if you take the light curve of them, they have a particularly distinctive light curve, which I've forgotten to include here. But anyway, another one is a Roche limit binary. So this is where they are close enough that the gravitational influence is actually meaning that one star can steal material from another star, that the gravity is sufficient to overcome one star's hold on its own material, and the other star can start stealing it. So this is sort of shown in this nice diagram here of how two stars might evolve. So this is in the Roche limit case. You can see these two are actually separated, but as they evolve, and this one perhaps gets into its red giant phase, it gets to this point in C where it's actually filling this black line, which is its Roche limit, which you can calculate. And at this point, it overflows it. And now any material that's in there is start to get stolen by this other star. And this star starts to steal it all. And this can actually end up with what's called a common-centered star. Oh, no, I've forgotten what it's called. Well, I've got to write it down. But it's when the actual two stars appear as one. So this is a double star that actually, no matter how good your resolution is just seen as one star, because one star is actually moving around in the envelope of the other. Oh, common envelope. That's the name for it. So it's a very distorted thing, but there are actually two stars within this common cloud of gas which is circling around each other.
And is this a one-way process, or does it reverse and start again?
I think it's probably temporary in terms of astronomy, because it usually happens with the red giant phase. So it swells up and grows, envelops the other one, but eventually it's going to give up and collapse down to probably a white dwarf, and then they will become two distinct stars again at that point. But for a while they can move around. And of course, a red giant is very, very tenuous in its outer atmosphere, because when the sun comes to the end of its life, it swells up to a red giant, which will probably enclose the Earth. But it's the same amount of material, so it's now really not nearly as dense as it used to be when it was a compact star. So quite easily you can have planets and other things circling within this stuff. Extremely hot by then, but there you go. And then we can get to also cataclysmic binaries, which is, again, this sort of Roche overflow thing where one can steal from the other, but in this case, you can actually see them. So this is the case in this case of a white dwarf stealing material from a normal star. So it gets sort of filtered off and swirls around into this accretion disk, which slowly spirals in onto the white dwarf. But where the material moves from the normal star into the accretion disk, you get this big hot spot here, which is particular signature. So you can't see these because you don't typically have the resolution to split these two stars, but you can see something happening in a particular wavelength. You can see this big spike of sort of heat from where this material lands on here and gets something very hot. Now, I think we're back to James with Have a Go Yourself.
Yes. Right, so this is about what we can all do. So double stars generally are pretty bright, so not usually hindered so much by light pollution. You can do this with most types of telescopes and even binoculars. As I said earlier, you can do it for fun, just to make a list of some doubles that you'd like to have a go at splitting one night, or you can do this over a long period of time and log the differences in separation and position angle and observe how these binary systems change over months, years, sort of time frame. So here's one for all of us, Epsilon Lyrae. So we need to find the summer triangle, which is still visible if you look towards the west as sun, just after sunset. You'll still be able to see Vega, Deneb and Altair. And if we zoom in, here's a zoom in view of Vega and Deneb, and there's a line between them, and they're about 27 degrees apart. And if you look towards Vega, the first bright star along that line is Epsilon Lyrae. And if you look at that in a bit more magnification, you'll see that Epsilon Lyrae is actually 2 stars. And it's called the double double, and that will become relevant in a minute. So you can see it's reasonably close to Vega. It's about 75 arc minutes away. And if we zoom in a bit closer on Epsilon Lyrae, you'll see that this double is actually 2 pairs, or 2 pairs. Does that make sense? 2 pairs. There's 4 stars. The double star we saw earlier actually is 2 lots of 2. And the separation between them is about 2 arc minutes. So this is really pushing naked eye visibility. So if you can split Epsilon Lyrae into 2, then you've got pretty good eyesight, and the seeing is pretty good wherever you are. And then it's not easy to do, but the actual separation between each of these pairs is about 2 arc seconds. So that is really large telescope territory to split these accurately. Now the other star I'm just going to finish on is Sirius. So we've got Orion high on the right, and the belt stars point down towards Sirius, the brightest star in the sky. And in fact, Sirius is a double star. The Sirius A, which is the brightest star we all know about, and Sirius B, which is called the pup, because Sirius is the dog star. The pup, I think, pertains to the fact it's a little dog. And you can see on this graphic here that over the course of about 50 years, the pup orbits Sirius as viewed from Earth. On this graphic, it starts at the year 2000, goes all the way around to where we are now, and back down to 2048. So about 50 years, it goes in this orbit around Sirius. Sirius is pretty bright, -1, and the pup is relatively faint, magnitude 8.4. But as you can see at the moment, the pup is probably getting to about greatest separation from Sirius. So I suspect 2025 will be the greatest separation, and that's about 10 arc seconds. So that's easily achievable. And this is just showing the angle of movement. And here we've got an image by our own Gareth and Richard. And you can just see Sirius B, the pup, in that position there. And they took this in 2019, last year, with Gareth set up in his garden, which is a great achievement because it's a very difficult thing to identify. And it's one of the challenges that amateur astronomers try to achieve, is to either visualize the pup or to image it. And Gareth and Richard have achieved that. They've got that ticked off on their bucket list. So well done. Now, the other thing that's in the literature is something called an occulting bar. And this is some kind of strip which goes across the eyepiece, and you can position a brighter star or a planet behind that strip, so it doesn't glare so much in your eye, and that allows you to see things orbiting that bright object, which you might not otherwise see. So planetary moons or double stars. And this is one I made earlier, as they say. I got a bit of foil and cut it and taped it on the telescope end of an 8mm eyepiece. The edge is a bit jaggedy, so I think this version will cause a lot of diffraction, and it will probably make the situation worse than better. I'm going to have a go with it at some point, but so it's something you can try and do yourselves. So there are lots of books on double stars. It's a very popular field of amateur astronomy. and there are lots of online resources. And we hope that you've all learned a little about double stars and will be enthused to maybe look them up in Roy's Sky Notes and go and have a go at maybe Epsilon Lyrae while it's still visible, or even Sirius as the winter carries on, and see if you can beat Gareth's and Richard's attempt at finding the pup.
Oh, very good. Just while we're here, I just thought a nice little anecdote to finish up with. So one of the objects in the Messier catalogue is called Messier 40. And this is an object that doesn't actually seem to exist. It was something, I think, pointed out to Messier that somebody thought they'd seen something there, and he went and had a look, and he couldn't see anything in the normal fuzzy type thing, but he did see a double star there, so it became known as M40's double star. And people have long wondered whether this is actually an optical or a gravitationally bound system, and they are sufficiently close together that nobody was quite sure. But in, let me see, 2017, Mike Merrifield, who you might know, who's given talks to Plumtree a few times, downloaded the Gaia data, which is a map of the Milky Way with positions of all the stars, and went and investigated this to see if it actually was just a visual binary or a definite binary star. He makes a series of videos called Deep Sky Videos, which he's gone through, him and some other people gone through all the Messier catalogue. So he was looking at Messier 40 to see what he could talk about, because there's not very much to talk about otherwise. Anyway, it appears that it's is not a connected system. It is just purely optical double. And he wrote a paper on it, which was the shortest paper he's ever written, because it was only a page long. And it's called Gaia Shows the Messier 40 is Definitely Not a Binary Star. And he submitted it to a journal, and they said, no, it's far too short to publish because it's only a page. So he found another journal and did submit it to that one. And we also submit papers to a place called the Archive, which is, as its name might imply, an archive of all papers. So you often submit them there, and you can find them publicly. Anyway, it was refused there because they have a lot of automated systems that look at papers and try and get rid of rubbish. And they decided his was rubbish because it was only a page long, and nobody reputable publishes a paper just one page long. He then had somewhat of a dispute with the archive maintainers, and eventually they did get it accepted as a paper. So you can go and look it up now, and say just Google for Gaia Shows Messier 40 is Definitely Not a Double Star. So there you are, a little local interest. But double star science is still ongoing.
Well, it's interesting you mentioned Gaia, because Gaia is going to refine a lot of the double stars and potentially find a lot more.
Yes, indeed.
And I was reading earlier today, despite the fact there's no atmosphere for Gaia to look through, because of the size of the optics and the resolution limits, it's still only going to be able to identify separations of down to about 0.2 arc seconds, which is still inferior to ground-based, which get down to 0.02 arc seconds.
Yes, so, indeed. Yeah, it's not got a particularly big telescope on it.
No,
it's got a very big camera, but its telescope is pretty average.
Its advantage is it can do lots in very short periods of time.
Yeah, it maps the whole sky.
Right. Well, thank you, Julian.
Thank you, James.
Thank you, Richard and Lee, for helping in the background. And I think we'll open up for questions. Super. Let me just do some clicking. Super. Is the sound okay still, Julian? No, we've...
Sounds good to me.
Well, that's good. So we've got some questions in. Have you seen the first question from Chris S?
Chris, yeah. Do double stars start as singles and get attracted to each other, or are they born together in close proximity? I think it's probably, well, it's almost certainly the latter, in that most stars are formed in a big cluster. So they're formed by a huge cloud of gas that gets very cold and then collapses down and forms lots of stars. So some of them form right next to each other, and then they become a double star. This is probably also true of our sun. We probably started off with several other stars, very close proximity. But sometimes you can get triple and quadruple stars. But if you get too many of them together, then they tend to sort of argue and fight between each other. And usually some of them are losers in this battle, and they get kicked out of the double system and sent off to go and explore on their own. So that may well be what happened to our sun. There is a chance that another star will come across, just like another star might drift into the solar system, but it would have to be going at a particularly specific speed to actually be captured by our own sun and become a double star. So that's probably very unlikely, although never say never.
John has said we should get M40 reclassified as M for Mike.
I think he has.
Or Merrifield.
Merrifield, yes. He has as good a claim on it as anyone, I think.
I've put a hyperlink to the Merrifield paper. It's nice to be able to read a short paper which just gets to the point.
Yes.
So you can tell Mike I approve of this style of publications.
Oh, I certainly do.
Now Rhiannon's back with us.
Oh yes.
Hello Rhiannon. Is there a reason for the 1.22 factor in the Airy blob equation?
I'm absolutely sure there is, and it's probably just a constant to change things from whatever it is, wavelengths in probably nanometers to radians or something like that. I don't know exactly why it's 1.22, but it's probably just a conversion factor. A lot of time people just miss it out because it's almost the same as 1, so you might as well just, unless you're being very precise, you can just discard it and just go with 1. And you can also get rid of the sign on the other side as well, because typically you're dealing with very, very small angles, and a sine of an angle, sine of a very small angle is the same as just the angle itself, which I'm sure you know because you are now a up-and-coming physicist.
There you are, Rhiannon. Stuart Portier says, what fraction of stars are double or multiple?
I'm not sure. I've got a figure in my head that's somewhere between 1/3 and 1/2 or something like that, but that could be entirely way off. So I think we'd have to Google that one to be absolutely sure. I should have looked that up for this talk, but there's a lot of things I should have looked up for this talk.
Yeah. Well, this is good. Richard's started sharing some live footage of Mars.
Oh, yes.
So I'll keep an eye on the questions anyway. So for those who don't know, the shimmering image in the center is the live feed of Mars, and Richard has just done a quick process, he tells me, in another window of some of that data, and he's got this image here, and we can see the white southern polar cap at the bottom, small because it's southern hemisphere summer on Mars, and the southern hemisphere is the darker region. And what we can see here looks to be this dust storm which is evolving on Mars. Now a dust storm is something which happens on a pretty regular basis on Mars. They are small localized events, and then they expand and can become planet based, and all of the features of the planet are blurred out by dust. I'm just looking at, and yes, it is. So that is this newly evolving dust storm, which has been brewing for the last week or so, and you can see it's more yellow, if anything. You have to use the eye of faith, and what I can do is, if I can share, okay, Richard's disabled sharing, so I can't at the moment show you any other images of that, but that is that dust storm which people will be watching with interest, how it evolves over the coming days.
James, I've just set you up so you should be able to share that if you want to.
Okay.
I should say those images are taken just before the meeting started that we were showing in the introduction. So
Okay.
it's a mega quick process, and Mars at the time was right over the top of all my neighbours' houses. So the seeing was probably even worse than it otherwise is. But I thought it'd be nice to have a quick process of what we were showing before the meeting. So that's just at the bottom left.
Yeah, definitely.
So let me share another screen. So can you see this image now, Julian?
I can. Ooh,
This is a Damien Peach image.
Yeah, I was about to say that must be a peachy image.
From 2 nights ago. And again, if you can remember on Richard's image, we've got that south polar cap, a lot of the darker detail of the southern hemisphere, and then can you make out this area here, which is a different yellow to other parts of the planet? So it's mostly on this part of the southern limb, and there's some others. I've picked some others up whilst. So here's a drawing from Paul Abel. When was this one from? Where's the date? November 18th. So last night. Now this time we've got south is up, and again you can see Paul's used a subtle different yellow. That seems to be extending down towards the equator of the planet here. So Paul Abel from Sky at Night fame and otherwise on the TV, who's based in Leicester, he's an academic in Leicester. He does a lot of sketching of planets and the moon, and this is a recent observation he's made. And then we're also in National Astronomy Week this week, and each night between 7 and 8 there's some live footage of Mars. The whole theme of the week is Mars, and this guy here, Agapios, is in Cyprus, and I was on with him I think 2 nights ago, and he got this excellent data. His live data is this smaller image here in the center, and again with the eye of faith, here we've got south at the bottom. With the eye of faith you can see that there's something there, and when he processes his data he gets a much cleaner image. This larger one here, again the south pole there, so south is bottom, and then this creamier patch showing the dust storm evolving there. And there was another sketch from Chris Nuttall in York on the Cloudy Nights forum. Again we've got south up, and this is again similar to Paul Abel's. We've got an extension of that dust storm coming down towards the equator. So let's go back to Richard's. Richard, can you take this thing back to your live feed? And here we can see the central images shimmering. This is due to the atmospheric disturbance, the seeing conditions, we call them. The planet constantly moving and shaking and very hard to focus and refine detail. So that's brilliant that you got that tonight, Richard.
Yeah, very well done.
So let's see.
So another question there by Anthony.
Yeah.
I read it's possible there are 100 million stars in binary systems with black holes in the Milky Way alone. What do you think? I have to say I don't know, but doing a quick calculation in my head, there's about 400 billion stars in the Milky Way. So that would be about 1 in every 1,000. I'm suspecting that might be a little high, but not beyond the bounds of possibility. So yeah, it's quite possible, I guess. I don't know that we know extremely well the frequency of black holes, but we're tending to think they're more common than we thought now, after experiments like LIGO have started to pick up quite a number of them in other galaxies, but we can extrapolate to our own.
Can these extra black holes account for any of the missing matter?
I don't think so. You need about 5 times as much matter to get rid of dark matter. So you need like 5 black holes to every star we can see to get close.
Right.
Something like that anyway. Probably not quite that much because they tend to be heavier. But
so Shirley says, great talk, thank you.
yes, thank you, Shirley.
Of the live stream of Mars, and great to see Richard and Gareth's pup. Yeah, that was good.
Very good.
Hopefully this winter we'll all have a go at the pup. Jeremy says definitely the dust storm on Richard's images, so that's good. Fascinating to see the dust storm. Yeah. Have you seen the French people's images of complete rotation as a stereo pair? That's from Fred. I've not seen that.
No, I haven't seen that.
But interestingly, one of the PhD students in Mike Merrifield's department did a 3-hour rotation of Mars.
Yes. Yeah. Joel. Yeah.
Joel. Yeah. And I did an online interview with him earlier today, and Lee's going to edit that up and put some bits in, and we'll show that in a future plum tree. I'm hoping Joel will come along to one of these online meetings at some point and talk to us.
Sure, I can twist his arm.
Yeah. When are you moving to Cyprus? Well, I would like to. I told Agapios I was very envious of his stable seeing.
Mars is a lot higher up there, isn't it? Because they're further south.
And the jet stream doesn't have anywhere near the impact. Can you say anything about the distribution of multi-stars along the HR diagram, Julian?
That's putting me on the spot. I don't think I can. I suspect. So just thinking about this bit. So small stars are much more common than big stars. Big stars are quite unusual. In fact, stars smaller than the sun are probably the most common size to be made. The sun is a little large. It's not sort of extreme, but it's larger than the average star. So very, very big stars are very, very rare. But on the other hand, they're very, very bright. So you tend to see them quite strongly. So I would suspect that you're much more likely to get pairs of small stars than you are pairs of large stars. But it's an area that's not really very well understood. Forming stars out of clouds of gas is a very chaotic process. So nobody quite predicts exactly what you're going to get. You can predict in general. There is a sort of a general equation that will say for a given cloud of gas, you're probably going to get this many small stars, this many medium-sized stars, and this many big stars, and you get very few big stars and you get many more small stars. But to be absolutely specific and say, well, how many of these you're going to get, we can't do the calculations or even simulations at the moment to give good answers to that. That's a long waffly way of saying I don't know.
I've had a look on Google, and there's a book, Multiple Stars Across the HR Diagram. It's 400 pages. It's Proceedings of an ESO workshop. So maybe
Right.
Stuart can get hold of a copy
and read through the 400 pages and summarize it for us.
Right. One, Richard's images show the phases of Mars less than full. Yep. So yes, Mars does show subtle phases, not as much as Venus, but it's currently, Richard is saying, 94.4% illuminated. Rob Dawes enjoyed it, that's good. And John's happy. And Herbal's happy, that's good.
Hooray.
People are happy.
That's
In a
good.
time of a world pandemic, people are happy, so that's good. And you've all got the link for Mike Merrifield's paper, which will take you about 5 minutes to read.
There will be a test on it later.
Yeah. So hopefully people are going to get out and have a think about double stars. I'll do a little write-up for the journal with some links.
Yes, definitely. Mars or an alcohol. If you've got good eyesight, you should be able to split those without anything.
Yeah.
I have to say my eyesight is not that good anymore. But I know it used to be used by the British Navy. So the people they put up in the crow's nest had to be able to split Mizar and Alcor to be given the watch out post.
Yeah. So the last time we were assembled at the observatory, I could split them at the start of the evening, but after several glasses of Chris's mulled wine, I was unable to split them, and I couldn't even find the pole star.
That's because you were face down by that point.
No drinking on the site, please. No. Right. Thank you, everyone. And people love the Mars. Have we got? Can we put Mars back up, Richard?
Oh, we can't now. I'm back inside from the cold.
Oh,
it's chilly.
Oh, get the cocoa out then.
Yeah.
Don't forget Alberio. Yes, John. We won't. Alberio.
Nice stars.
That's drifting further west, so we might have to wait till next year. Anything else? That's it from me. I'm just waffling on. Julian?
No, nothing else from me. Thank you.
Yeah, I'll just quickly go through what we've got coming up then. So meetings wise, the next meeting is on Thursday, the 3rd of December. That is Paul Money, and his talk is on the Vikings at Barsoon. So that sounds interesting. That talk's not going to be on YouTube. So Paul doesn't want his talks on YouTube. So that will be on Zoom. So all members will get sent details of how to log into that. If you've been enjoying all our meetings and want to join, we'll shortly be opening our membership here for next year. So do think about joining if you've enjoyed the talks. Our treasurer will be glad to take the money off you. So that's £30 for adults and £5 for students if you're interested. All the details are on the NAS website, so do have a look there. And you can join the society. We'd be delighted if you would like to join us. Obviously, we'll be online for the next coming months, and then hopefully sometime later next year we'll be able to resume our normal meetings. And then our next Plumtree Social Practical Astronomy meeting is going to be on Thursday, the 17th of December. So that's our last meeting before Christmas, again at 8 p.m. And we're welcoming Mary McIntyre, and she's going to be doing a talk on astronomy sketching, and Julian's kindly offered to host that meeting. So that talk will be on YouTube, but we thought it'd be quite nice, as it's the last meeting before Christmas. After the talk, we're going to do questions and also just a chat for members on Zoom after the talk's finished on YouTube. So you can have to bring your own food and drink, unfortunately, but do join us after the meeting. We'll have a social chat on Zoom. And then just looking further ahead, so starting next year, we've got our postponed annual general meeting. That's going to again be on Zoom, so members will be sent details for that near the time. We'll be sending out all the various reports and papers ahead of that, I think sometime early December. So that'll be on Thursday, the 7th of January, again at 8 p.m. So that's NAS. James mentioned this in earlier. So the National Astronomy Week is this week. So there's a full programme of events. If you go to that website, astronomyweek.org.uk, there's loads of different talks. So there's lunchtime talks. I think there's certainly be one tomorrow aimed at sort of children. And then the evening, there's a talk at 6 p.m, followed by some live observing sessions. I think they start at 7. You can sign up and join on Zoom, but the talks actually are available on YouTube. If you go to the National Astronomy Week and search for them, you'll see the talks there. So you don't actually need to register. So do check out some of those. I think they run for Friday, Saturday and Sunday for the rest of Astronomy Week. But all the old talks from early in the week, if you've missed them, and the live telescope events, all actually on YouTube, so you can catch up if you've missed any of those. There's some really good talks to watch. So that's National Astronomy Week for the rest of this week, so do have a look at that. Okay, that's it tonight. Thank you all for watching. Really enjoyed the talk from James and Julian, so thanks very much for all their hard work putting that together, and also Lee for all his work in the background. I hope you enjoyed the live views of Mars. Sorry we couldn't show any more because it's clouded up now, but I think I'm too cold, and that'll perhaps do us for tonight. So yep, I hope we see you for our next meeting, which is on the 3rd of December. Until then, for myself, Julian and James, a very good night.